Welcome back to the Deep Dive. We are back in the virtual classroom today, continuing our rigorous journey through the Integrated Neurobiology, Structure, Function, and Pathology course. I'm your host, and I have to say, I am absolutely pumped to be back for this session.
It is good to be back. And strictly speaking, we are looking at the source material for Lecture 2 today.
Exactly, Lecture 2. Now, if you were with us for the last deep dive, we tackled Lecture 1, which was, well, it was a heavy lift. It was all about cellular neurophysiology membrane potentials, the Nernst equation, the Goldman equation, all of that really foundational biophysics.
We essentially built the battery.
We built the battery. And today, we are taking that battery and we are wiring the house. We are moving on to synaptic transmission and neurochemistry.
Which is really the logical next step, isn't it? In Lecture 1, we established how a single neuron generates an electrical signal, the action potential. But, a neuron in isolation is useless.
Right, it's like a telephone with no one on the other end of the line.
Precisely. It can ring all day, but if that signal doesn't transfer, there is no communication. Today, we look at how that electrical signal manages to jump the gap to the next cell.
And looking at the syllabus for the Integrated Neurobiology course, we are, as always, strict about following that specific progression. We're tracking the anatomical sequence of neuroanatomy through clinical cases by Blumenfeld, which gives us our map. But for this specific module for Lecture 2, we are integrating the cellular physiology from Costanzo physiology and the hardcore pharmacology from Ketzone pharmacology.
Right. It's an integrated approach. You can't understand the anatomy if you don't understand the wiring, and you certainly can't fix the wiring with drugs, which is what we do as physicians if you don't understand the chemistry. It all has to fit together.
So here's the mission for this deep dive. We have a set of 15 slides for this lecture in the source material. We're going to go through them sequentially, strictly following the slide order, the title, and the information. We're aiming for a physician-level understanding here, so we aren't going to skip the hard stuff. We're going to allocate significant time to really unpack the nuance of every single one of these slides.
Sounds like a plan. It's the only way to do it justice.
We've got some big themes to cover. The calcium trigger, which I know is huge, the difference between fast and slow receptors, the math of summation EPSPs versus IPSPs, and then my favorite part, the pharmacology. We're going to talk about where Botox, cocaine, and Curar actually do their work.
It's a fascinating lineup, the fundamentals and then the clinical application. Let's get started.
Okay, let's visualize slide 1. This is the title and learning objectives slide. But visually, for you listening, I want you to imagine a kind of split screen diagram. On one side, you've got a presynaptic terminal. It's the sender, and it's releasing these little bubbles, vesicles. On the other side, you've got the postsynaptic membrane, the receiver, and it's just studded with receptors.
That visual is key because it frames the entire lecture. We are moving from the biophysics of the membrane, which we did last time, to what you could call the chemical handshake between cells.
A chemical handshake. I like that. So the slide lists 3 main objectives based on Costanzo Chapter 1 and Katzing Chapter 21. What are the 3 pillars we need to nail down here?
Okay, so the first pillar is the mechanism of release. Specifically, and we're going to hammer this point home, we need to understand the absolute dependence on calcium 2+. No calcium, no signal. That is a non-negotiable rule of the nervous system.
Okay, calcium is king. We're going to drill that in. What's number 2?
Number 2 is receptor kinetics. We need to contrast ionotropic receptors, which are, incredibly fast, with metabotropic receptors, which are much slower. Understanding the difference between those two is crucial for understanding everything from a knee-jerk reflex to the formation of a long-term memory.
And the third pillar?
The third is the ionic basis. We need to understand what makes a signal excitatory and EPSP versus what makes it inhibitory and IPSP. Why does one signal tell the neuron to fire and another tell it to shut up? It all comes down to which specific ions are moving across the membrane.
I love the hook on this slide here. This isn't just biology. This is the operating system of the brain. It really is, isn't it? I mean, everything from me moving my hand to scratch my nose to me remembering what I had for breakfast this morning, it all starts with this fundamental mechanism.
It really does. This is the fundamental unit of computation in the brain. The neuron is the transistor, you could say, and the synapse is the logic gate. Everything else is built on top of this.
All right, let's move to slide 2. The chemical synapse architecture. We need to
Yeah.
set the scene anatomically. We're looking at the structure of the synapse itself,
Right. And the most prominent feature you see on this slide, the first thing you'd notice, is the synaptic cleft. It's a gap about 20 to 40 nanometers wide.
which is tiny, but it's huge in biological terms. I mean, to an electron, that's a canyon, right?
It absolutely is. And the key point is that it prevents direct electrical continuity. The electrical current that's running down the axon, that flow of ions, it can't just jump across this gap like a spark plug. The resistance is far too high. It has to stop, and it has to change forms.
It changes from an electrical signal into a chemical signal. It's like driving a Ferrari at 200 miles per hour and suddenly hitting a river with no bridge. You have to get out of the car, get on a ferry, cross the water, and then, get into a different car on the other side.
That is a perfect analogy. And that ferry ride, that takes time. The slide highlights this concept of synaptic delay. It takes approximately 0.5 milliseconds for the release, the diffusion, and the binding of the neurotransmitter.
Half a millisecond doesn't sound like much to me.
It doesn't to us living in the macro world. But in a neural circuit, it's an eternity. Conduction along the axon is incredibly fast, nearly instantaneous over short distances. This chemical step, this ferry ride, is the rate-limiting step. It's the traffic jam in the commute.
So if you have a reflex pathway like pulling your hand away from a hot stove, that needs to be as fast as humanly possible.
Exactly, and that's why reflexes are usually monosynaptic or dissynaptic. They involve only one or two synapses. You minimize the number of ferry rides to keep the speed up. If you had to think about it, if you had to use your cortex, which involves thousands and thousands of synapses, your hand would be seriously burned before you ever moved it.
Okay, that makes perfect sense. Let's look at the components listed here on the slide. On the presynaptic side, we have mitochondria and synaptic vesicles.
The mitochondria are there because this process is incredibly energy expensive. We are running a factory here. Synthesizing neurotransmitters, packaging them into vesicles, pumping ions back and forth to reset all the gradients, that all requires a constant supply of ATP.
So the mitochondria are the power plants and the vesicles.
The synaptic vesicles are the storage units. They are little membrane-bound spheres, just packed full of the chemical messenger, ready to go.
And on the postsynaptic side, we have the active zone and the postsynaptic density.
So the active zone is actually on the presynaptic membrane. It's the launch pad where the vesicles dock. It's very precise. The vesicles aren't just floating around randomly. They're queued up right at the door.
Waiting for the signal.
Exactly. And the postsynaptic density is on the receiving side. It's a thicket of receptors and scaffolding proteins just waiting to catch the signal. It's like a catcher's mitt, perfectly positioned.
Moving on to slide 3, and this is where the action happens. The title is Excitation-Secretion Coupling, the calcium trigger.
This is arguably the most critical slide for understanding the physiology of this whole process. We're tracing the signal. The action potential arrives at the terminal, and this causes a depolarization.
So the voltage goes up. The inside of the membrane becomes more positive.
Right. And that voltage change opens a very specific set of gates, the voltage-gated calcium channels. Specifically, in the nerve terminal, we are usually talking about N-type or PQ-type channels.
Now, in the last lecture, we talked a lot about sodium rushing in to cause the action potential. Why is calcium so special here? Why not just use sodium again to trigger the release?
Because of the gradient. This is just fascinating physics. The extracellular concentration of calcium is about 2 millimolar. That's 10 to the minus 3. The intracellular concentration, the free calcium inside the cell, is about 100 nanomolar.
Whoa, wait. Nanomolar, not millimolar, nanomolar.
Yes, nanomolar, 10 to the minus 7. The cell spends a huge amount of energy actively pumping calcium out to keep the inside almost completely empty of it.
So what's the difference in concentration then?
It's a massive difference. The concentration outside is roughly 20,000 times higher than it is inside.
20,000 times.
Correct. So when those voltage-gated calcium channels open, calcium doesn't just flow in, it rushes in with tremendous force. It's an absolutely massive electrochemical gradient. It's like opening the airlock on a spaceship. The vacuum sucks you out, or in this case, the gradient drives calcium in with incredible violence.
So it floods in, and that flood is the trigger. The slide details the molecular machinery here. That intracellular calcium binds to a sensor protein called synaptotagmin.
Synaptotagmin. It sounds like a transformer, and it kind of acts like one. It is the calcium sensor, and it sits right on the vesicle membrane. When it detects this rush of calcium, it changes shape, and that shape change triggers the snare complex.
Snares, those are the proteins that act like twist ties, right? I've heard that analogy.
Think of them more like a winch or a zipper. You have V snares on the vesicle and T snares on the target membrane. They twist together, they interdigitate, pulling the vesicle closer and closer and closer to the cell membrane. But they are stalled just before fusion.
Waiting for the signal.
Right. They're primed and ready. When calcium hits synaptotagmogen, it releases the brake. The snares zip up the rest of the way and pop the membrane's fuse. The vesicle opens up and dumps its entire contents into the synaptic cleft.
And the slide has a clinical note at the bottom in bold. Without calcium, there is no release.
That is absolute. You can have all the action potentials you want coming down the axon, but if you block those calcium channels, or if you're in a solution with no calcium outside the cell, the signal dies right there at the terminal. The doorbell rings, but no one ever opens the door.
Let's go to slide 4, quantal release and vesicle biology. This sounds a bit like quantum physics. Quantal release.
It does, but it's a biological concept.
Yeah.
It was discovered by Sir Bernard Katz in the 1950s, a Nobel Prize-winning discovery. He noticed that neurotransmitters aren't released as a continuous stream, like water from a hose. They come in discrete packets, or quanta.
And one quantum equals the contents of one vesicle.
Exactly. One quantum.
Yep.
The contents of one synaptic vesicle. It's a standardized amount.
The slide mentions miniature potentials, or minis. What are those?
Well, Katz was recording from the postsynaptic membrane, and he saw that even when the neuron was at rest, totally quiet, occasionally, by pure random chance, just thermodynamic noise, one single vesicle would fuse and release its payload.
Just one.
Just one. And this creates a tiny blip of a depolarization on the postsynaptic membrane. He called it a miniature end plate potential, or MEPP.
So it's like a dripping faucet.
That's a perfect analogy. It's a drip. It's subthreshold. It doesn't cause the neuron to fire. But it tells us that the packaging is discrete. Katz saw these blips of a consistent size and realized the signal wasn't analog, it was digital packets.
And how does that contrast with an evoked potential?
An evoked potential is what happens when the action potential hits. Now you have synchronized the release. Instead of one random drip, the calcium flood causes hundreds of vesicles to fuse almost simultaneously. It's not a drip, it's a bucket dump.
And all those quanta sum up.
They sum up to create a real large signal that pushes the postsynaptic cell to its threshold.
Got it. So minis are the background noise, the proof of concept, and evoked is the actual message. Now, slide 5. Termination of the signal.
This is a problem of cleanup, really. You've released this chemical, it is bound to the receptors, it's done its job, now you have to get rid of it.
Right, because if you don't, the receptor just stays activated forever.
Exactly. If you don't turn off the signal, the system fails. Imagine pressing a key on your keyboard and the letter just keeps typing forever. EPA, You can't type the next letter. In the brain, if you don't remove the transmitter, the neuron desensitizes, or in the case of muscles, you get a tetanic contraction, a cramp.
The slide lists 3 mechanisms referencing the physiology pearls. What's the first one?
Mechanism 1 is enzymatic degradation. The classic example here is acetylcholine, or ADAA. In the synaptic cleft, there is an enzyme waiting called acetylcholinesterase, ACE.
The molecular scissors.
Precisely. It sits right there in the gap. As soon as ACE binds and does its job, this enzyme grabs it and splits it into choline and acetate. And once it's chopped up, it can't bind to the receptor anymore. Game over. The signal is terminated.
Okay, that's very efficient. Mechanism 2 is diffusion.
The simplest of all, simple physics. The transmitter just floats away. It diffuses out of the high concentration of the cleft and away from the active zone, so it can no longer find the receptor. It's a bit inefficient, but it works for some larger molecules like neuropeptides.
And mechanism 3, which I know is a huge one for pharmacology, active transport or reuptake.
This is the most common method for the small molecule transmitters in the brain, like dopamine or serotonin. Why waste the molecule? It took energy to make it. So the presynaptic terminal, or sometimes a nearby glial cell, has these little vacuum cleaners, transporter proteins that actively pump the transmitter back inside to be recycled and repackaged into new vesicles.
And the slide notes this is a major drug target.
Huge, absolutely massive. SSRIs for depression, cocaine, tricyclic antidepressants, they all work right here on these pumps. They jam the vacuum cleaner so the neurotransmitter stays in the carpet, so to speak, for longer.
We'll definitely get to those in the pharmacology section. That wraps up section 1. We've covered the presynaptic side for this ender. Now we're moving to section 2. Postsynaptic mechanisms, starting with slide 6. Receptor classification, ionotropic versus metabotropic.
This is the listening side of the conversation. The neurotransmitter has crossed the gap. Now it has to talk to the next cell. And it does that through 2 very different types of, Phones.
Let's start with the ionotropic ones. These are also called ligand-gated ion channels.
The key here is structural. The receptor is the channel. It's all one single piece of machinery. Imagine a door with a handle built right into it. The neurotransmitter, the ligand, binds to the handle, turns it, and the door swings open immediately. An ion channel opens.
Oh, it's fast.
Extremely fast. We're talking milliseconds. The examples listed here are the nicotinic ACE receptor, which drives all your muscles, the GABA A receptor, and the NMDA and AMPA glutamate receptors. When you need speed like playing the piano or pulling your hand away from that hot stove, you use ionotropic receptors.
Okay. Contrast that with metabotropic receptors or G-protein-coupled receptors, GPCRs.
Here, the receptor is not the channel. It's a manager. It sits on the surface of the cell. When the neurotransmitter binds to it, it doesn't open a door itself. Instead, it turns around and activates or kicks a G protein on the inside of the cell.
And that G protein goes off to do the work.
Right. It's a cascade. The receptor activates the G protein. The G protein then goes and activates an enzyme. The enzyme produces what we call second messengers molecules, like CAM-MP or IP3. And those messengers then go and phosphorylate other channels to open or close them.
That sounds incredibly complicated and, well, slow.
It is slow. It takes seconds to minutes for the full effect. But the advantage is amplification. One receptor binding one molecule can trigger the production of thousands of second messenger molecules inside the cell. It's like one person making a phone call that mobilizes an entire army.
And this is for modulating the state of the brain.
Exactly. Things like mood, hunger, alertness, learning. The slide lists examples: muscarinic ACE receptors, the GABA B receptor, and all the dopamine receptors.
It's interesting that dopamine is almost entirely metabotropic.
It is, and that explains a lot about why dopamine affects mood and drive and motivation rather than, say, immediate muscle twitches. You don't twitch with happiness. You experience a prolonged shift in your brain's state. That's a metabotropic effect.
Now, slide 7. This is marked as a gap transition slide. The source notes that we are jumping from types of receptors to the electrical result of receptors.
Right, so we need to bridge this. We've just talked about the hardware, the protein structures themselves, the ionotropic versus the metabotropic receptors. Now we need to talk about the software, the actual electrical changes they produce in the postsynaptic cell. We are moving from structure to function.
So when these receptors are activated, what happens to the voltage? That brings us directly to slide 8, the excitatory postsynaptic potential, EPSP.
An EPSP is a change in voltage that makes the neuron more likely to fire an action potential. It pushes the membrane potential, the VM, closer to the threshold.
So if the resting potential is at negative 70 millivolts and the threshold is at negative 50, an EPSP is any little depolarization that pushes you up from negative 70 toward negative 50.
Correct. It's an excitatory push, a transient depolarization.
The slide explains the ionic mechanism. It says opening of non-selective cation channels. What does that mean?
This is a subtle point that trips up a lot of students. We usually think of channels as being for one specific ion, like a voltage-gated sodium channel. But many of these excitatory receptors, like the nicotinic receptor or the AMPA receptor, are non-selective. When they open, they let both sodium, Na+, and potassium, K+, through at the same time.
Okay, so if both are moving, why does the cell depolarize? Sodium is positive and wants to come in. Potassium is positive and wants to go out. Don't they just cancel each other out?
That's the tug of war that's mentioned on the slide. This is a brilliant question, and the answer comes down to driving force. At the resting potential of negative 70 milliV, sodium is very, very far from its equilibrium potential, which is around plus 60 milliV. It has a huge desire to get into the cell.
Okay, so a huge pull inwards for sodium.
A huge pull. Meanwhile, potassium is actually pretty close to its equilibrium potential of negative 90 milliV, so it only has a weak desire to get out.
So sodium just pulls harder.
Sodium wins the tug of war, hands down. The inward current of positive sodium ions is much, much stronger than the outward current of positive potassium ions. The net result is positive charge entering the cell, depolarization.
And the slide mentions that the reversal potential is around 0 milliV.
Right. That's the voltage at which the tug of war would be a tie. So the channel always tries to pull the cell's voltage towards 0 milliV. Since 0 milliV is way above the threshold, this is a strongly excitatory signal. Agents
listed are glutamate and acetylcholine at those nicotinic receptors. Now let's flip the coin. Slide 9, the inhibitory postsynaptic potential. IPSP.
An IPSP is a transient hyperpolarization. It pushes the membrane potential away from threshold, making it harder to fire, or at the very least, it creates a shunt that prevents it from moving up.
The slide details 2 ways to do this. Mechanism 1 is opening chloride channels.
This is how GABA A receptors work. Chloride is a negatively charged ion, and its equilibrium potential is usually around -70 milliV, or even a little more negative, like -75 milliV.
So if you open the door, chloride, being negative, flows in.
Right. If the cell is at rest at, say, -65 milliV, and you open a chloride channel that wants to be at -75 milliV, chloride will flow in, making the inside more negative. It hyperpolarizes. More importantly, it acts as a clamp.
Oh, clamp.
Yeah, we call this shunting inhibition. Imagine you're in a boat with a big hole in it right at the waterline. Even if you try to bail water out to raise the boat, which is like an EPSP trying to depolarize the cell water, just rushes back in through the hole to keep it level, the open chloride channel clamps the voltage down near the resting potential.
That makes a lot of sense. So what's mechanism 2, opening potassium plus channels?
This is how GABA B receptors work. Remember, GABA B is metabotropic. It activates a G protein that then goes and opens a specific type of potassium channel.
And since potassium is high inside the cell,
it flows out of the cell, taking its positive charge with it. If you lose positive charge, the inside of the cell becomes more negative. The cell hyperpolarizes, moving further away from threshold.
and the main agents for this are GABA and glycine.
Correct. Glycine is the major inhibitory transmitter in the spinal cord, and it works via chloride channels, just like GABA as in the brain.
Okay, we've covered the presynaptic release and the postsynaptic response. Now we get to the really complex stuff. Section 3. Integration and plasticity, starting with slide 10, synaptic integration summation.
This is where the neuron acts like a tiny computer, or maybe a better word is an integrator. A single neuron in the cortex might have 10,000 inputs synapsing onto it. Some are shouting fire, the EPSPs. Some are shouting don't fire, the IPSPs. The neuron have to listen to all of them and make a single decision.
The slide uses the analogy of a judge listening to thousands of lawyers.
It's a good one. A single EPSP is usually tiny, maybe half a millivolt. It's rarely enough to reach threshold on its own. It's like one lawyer whispering in a crowded courtroom. The judge isn't going to make a ruling based on that. You need summation.
And there are 2 types listed, spatial summation and temporal summation. Let's start with spatial.
Spatial summation is when inputs from different locations, different synapses on the dendrite, arrive at the same time. You have 3 different excitatory neurons firing at once onto our target neuron. Their individual small EPSPs add up. 1 + 1 + 1 = 3. The judge hears 3 lawyers all shouting the same thing simultaneously. That gets attention.
And temporal summation.
Temporal means time. This is rapid-fire input from the same presynaptic neuron. Bam, bam, bam. If the signals arrive fast enough before the membrane has had time to recover and repolarize from the first one, they piggyback on each other. The second EPSP builds on top of the first.
The slide mentions the time constant, which is represented by the Greek letter tau.
That's a biophysical property of the membrane. It's a measure of how quickly the membrane forgets the previous signal, how fast the voltage decays back to rest. If the membrane holds onto the charge for a long time, constant temporal summation is much easier. If it forgets instantly, you can't summate in time.
Fascinating. Now, let's move to slide 11, presynaptic inhibition. This looks like a complicated wiring diagram on the slide. An axoaxonic synapse.
This is some really advanced circuitry. Usually we think of an axon synapsing onto a dendrite or the cell body. That's axodendritic or axosomatic. But here you have an inhibitory neuron's axon terminal touching the axon terminal of another excitatory neuron.
So it's not inhibiting the cell body, it's inhibiting the terminal itself.
Exactly. It's like cutting the phone line before the call is even made. Let's say neuron A wants to excite neuron B, but a third neuron, neuron C, synapses directly onto neuron A's terminal. Neuron C releases an inhibitory transmitter, like GABA.
Okay, so GABA is released onto the presynaptic terminal. What does that do?
It activates receptors on neuron A's terminal, often GABA B receptors, and this can do one of 2 things. It might open potassium channels, hyperpolarizing the terminal slightly, but more importantly, it often inhibits the voltage-gated calcium channels we talked about back on slide 3.
So even if the action potential comes firing down neuron A.
The calcium channels don't open as effectively, or fewer of them open. Less calcium influx means less neurotransmitter release from neuron A.
So neuron B either gets a much weaker message, or it never even hears the message at all.
Precisely. The volume is turned down at the source. It's a very specific way to silence one input without shutting down the entire neuron.
And the slide lists the clinical relevance. This is how our body modulates pain signals.
Yes. This is a key mechanism in the gate control theory of pain in the spinal cord. And it's how opioids work. Opioid receptors are often located presynaptically on the terminals of pain fibers. When you take morphine, it activates these receptors, which then inhibit the calcium channel so the pain signal is never released onto the spinal cord neuron. It's not that the brain ignores the pain, the signal simply never arrives.
That is incredible. It's not an on-off switch, it's a volume knob.
It's a very precise volume knob.
Next up, slide 12. Glutamate in synaptic plasticity, LTP. This is the big one. So the molecular basis of learning and memory, right?
It is long-term potentiation, or LTP. It's the process of an activity-dependent strengthening of synapses. The famous saying is, neurons that fire together, wire together. This is the mechanism for how that happens.
And the star of this show, according to the slide, is the NMDA receptor. It's called the coincidence detector.
The NMDA receptor is a truly unique and elegant piece of molecular machinery. It's a glutamate receptor, so it's ionotropic. But it has a special problem. At the normal resting voltage of the cell, its ion pore is clogged by a magnesium Mg2+ iollars.
Like a cork stuck in a bottle.
Exactly. So even if glutamate binds, the key turns in the lock, the channel won't open because this magnesium cork is stuck in there, physically blocking it. The only way to pop that cork out is to depolarize the membrane.
How does that work?
The inside of the cell has to become positive enough to electrostatically repel the positively charged magnesium ion and push it out of the pore.
I see. So you need two things to happen at the same time. You need glutamate to bind, which tells you the presynaptic cell is active. And MODI, you need the postsynaptic cell to already be depolarized from some other input, which tells you the postsynaptic cell is also active.
Coincidence. Both cells are active at the same time. The presynaptic cell is talking and the postsynaptic cell is listening intently. When that coincidence happens, the magnesium pops out and the channel finally opens.
And what comes in when it opens?
Calcium. And this is the magic. The calcium that rushes in through the NMDA receptor acts as a powerful second messenger. It activates a whole cascade of kinases enzymes like CAM-KII, which then do things like tell the cell to insert more AMPA receptors into that same synapse.
So the next time the signal comes,
The synapse is stronger, there are more receptors waiting to catch the glutamate, the response, the EPSP, is bigger. That is the early phase of LTP, the strengthening.
Yeah.
And if the signal is strong and repeated, that calcium signal can eventually travel to the nucleus and trigger gene transcription to build entirely new synaptic structures. That's the late phase.
that is how you store a memory for a lifetime.
From a magnesium cork to a lifelong memory, it's beautiful, elegant engineering.
All right, we are entering the final stretch, section 4, clinical pharmacology, starting with slide 13, pharmacology of the presynaptic terminal.
Okay, now we get to play doctor. How do we hijack this beautifully engineered system? We look at the life cycle of the neurotransmitter and we find ways to attack it at every single step.
Okay, step 1 on the slide, synthesis inhibition. The drug mentioned is metarocene.
Right. Metarocene blocks an enzyme called tyrosine hydroxylase. That's the rate-limiting enzyme for making dopamine and norepinephrine. If you block that, you shut down the factory. We use this in rare cases of tumors called pheochromocytomas that produce massive amounts of these catecholamines.
Okay, step 2, storage inhibition with the drug reserpine.
Reserpine is an old drug, an old antihypertensive, but it teaches us a lot. It blocks the VMAT, the vesicular monoamine transporter. That's the pump that loads dopamine and norepinephrine into the synaptic vesicles.
So the neurotransmitter gets made, but it's just sitting around in the cytoplasm.
Exactly. And in the cytoplasm, there's another enzyme, MAO, that just eats it up, so the vesicles end up empty. When the nerve fires, it's shooting blanks. This causes a massive depletion of norepinephrine and dopamine. It lowers blood pressure, but it also famously caused severe depression because you've depleted the brain's happy chemicals.
Okay, step 3, release inhibition. Botulinum toxin or Botox?
Botox is a release inhibitor. It's a protease, an enzyme. It actually gets inside the presynaptic nerve terminal and it physically cuts the snare proteins.
The winch, the zipper we talked about earlier.
Yes. If you cut the winch, the vesicle cannot dock and fuse with the membrane. No fusion means no acetylcholine release. And if there's no assay, the muscle cannot contract. The result is flaccid paralysis.
Which is why it smooths wrinkles. It paralyzes the tiny facial muscles.
Precisely. And on the flip side of that, we have release promoters like amphetamines. Amphetamines are fascinatingly sneaky. They are release promoters. They get taken up into the terminal by the same transporter that does reuptake. Then they get into the vesicle and they actually displace the norepinephrine and dopamine. This whole process causes the transporter to run in reverse, effectively pumping the neurotransmitter out into the cleft, even without an action potential.
So you just get this massive non-physiological flood of norepinephrine and dopamine, which explains the focus, the energy, the euphoria.
A total hijacking of the normal release mechanism.
Slide 14, pharmacology of the synaptic cleftin receptor. Now we are outside the cell, in the gap.
Right. Let's look at reuptake inhibition, the vacuum cleaner analogy we mentioned earlier. If you block the vacuum, the dirt, which is the neurotransmitter, stays on the rug for a lot longer.
And the slide lists cocaine and TCAs, tricyclic antidepressants.
Both of these block the reuptake transporters for the monoamines, norepinephrine, dopamine, serotonin. The signal stays in the cleft longer, banging against the postsynaptic receptors again and again and again. That's the high of cocaine, a prolonged, intense dopamine signal in the brain's reward centers.
Okay, next up is degradation inhibition, EAT inhibitors.
These are drugs like neostigmine or, more sinisterly, organophosphate nerve agents. They block the enzyme acetylcholinesterase. They stop the molecular scissors from chopping up acetylcholine.
And the slide mentions a key clinical application, myasthenia gravis.
Right. In myasthenia gravis, the patient's own immune system destroys their nicotinic ACE receptors at the neuromuscular junction. They have fewer receptors, so they get profound muscle weakness. By giving an ACE inhibitor, we prevent the breakdown of ACE. We flood the cleft with a higher concentration of ACE for a longer time so that the few receptors that remain are much more likely to be activated. It restores muscle strength.
And finally on this slide, receptor blockade.
This is more straightforward. These are direct antagonists. Cure is the classic poison dart frog toxin. It sits on the nicotinic receptor at the neuromuscular junction and just physically blocks it. Acetylcholine can't bind. Result, paralysis.
And antipsychotics.
Many typical antipsychotics work by blocking dopamine D2 receptors in the brain, which is thought to reduce the overactivity in certain pathways that contributes to psychosis.
One last note here, autoreceptors with the example of clonidine.
Right. We mentioned this concept with presynaptic inhibition. The presynaptic terminal often has its own receptors that act as a feedback brake. The alpha-2 receptor is one of these for norepinephrine. When it gets stimulated, it tells the neuron, okay, that's enough norepinephrine, stop releasing so much.
So clonidine stimulates that brake.
Exactly. By stimulating this presynaptic alpha-2 receptor, clonidine tricks the neuron into thinking there's too much norepinephrine out there, so it shuts down its own release. That's why we use it to treat high blood pressure. It turns down the sympathetic nervous system's output.
We have arrived at the final slide, slide 15, summary and clinical pearls. Let's wrap this up with the big take-home messages for the physician-scientist.
Recap time. Let's boil it all down.
Key pearl 1, calcium is king.
Never, ever forget it. The action potential is just the courier delivering the message to the door. Calcium is the message that gets inside and makes things happen. Without that voltage-gated calcium influx, the electrical signal dies right there at the terminal. No calcium, no release, full stop.
Key pearl 2, receptor dictates action.
This is so fundamentally important. The neurotransmitter, acetylcholine, glutamate, whatever it is, it's just a key. The key itself isn't inherently excitatory or inhibitory. The lock it fits into, the receptor, determines what happens when the door opens.
That's the classic example.
Acetylcholine. It's excitatory at your skeletal muscles because it opens a nicotinic receptor, a sodium channel. But it is inhibitory at your heart because it opens a muscarinic receptor that's coupled to a potassium channel, which hyperpolarizes the cell. Same key, same molecule, completely different result because of the receptor it binds to.
And key pearl 3, integration.
The neuron is a sophisticated computer. It is constantly performing algebra at the axon hillock. +1 for every little EPSP bringing sodium in, -1 for every little IPSP bringing chloride in or letting potassium out. It sums them all up, both in space and in time. If that final sum hits the threshold,
It's binary, fire or don't fire.
based on an incredibly complex analog summation, it's a beautiful, elegant system.
That brings us to the end of a very dense lecture too.
We made it through the synapse, from the terminal to the receptor and everything in between.
Looking ahead to our next deep dive, lecture 3, we are going to expand on the pharmacology. We've touched on it today, but next time we are going deep into specific neurotransmitter systems, serotonin, dopamine, GABA, and the principles of neuropharmacology.
We'll look at the specific pathways in the brain, the diffuse modulatory systems versus the hierarchical point-to-point systems we mostly discussed today.
Before we sign off, any final provocative thought for our listeners to chew on?
I want you to think about the difference between the precise wiring we discussed today, this point-to-point synaptic transmission that's like one person whispering a secret to their neighbor, and what we call volume transmission. Imagine a neuron not whispering to its neighbor, but standing on a chair and shouting into a crowded room, releasing neurotransmitter that diffuses over a large area to influence thousands of cells at once. That is how a lot of our mood and arousal systems, like dopamine and serotonin, actually work. It's not a wire, it's a chemical soup.
I love that. The brain is a soup. A fantastic thought to end on. Thank you for joining us on this deep dive into the syllabus of integrated neurobiology.
My pleasure. See you in Lecture 3.
Dismissed.